Hi, I've got another top 5 Jellybean components for you. This is a follow-up to my previous video, which was very popular, linked up here and down below if you haven't seen it, where I looked at the top 5 Jellybean op-amp components. So today we're going to take a look at, ta-da, top 5 linear voltage regulators and references. So let's get down to it. Now, a Jellybean component is basically an industry standard component that has been around for a long time. It's been around forever. In the case of the first one we're looking at here, like been around for like 40 plus years. So a long time. And they're still used today as the go-to component for this particular function. They set the industry standard footprint, and they're available from many different manufacturers, including ones in China that you've never ever heard of. And you're practically guaranteed to be able to get these parts even in the current component shortages crisis, because there's just at any one point in time, even during times like these, there's going to be millions of these parts out there off the shelf you can use. And if you can't get a particular manufacturer, you can go to another one. And the whole idea of Jellybean components is that the specs are so generic that really it doesn't matter which manufacturer you actually use. You can just drop in a different manufacturer and you're good to go. So Jellybean components are just something that every hobbyist or engineer should have knowledge of. You should know the basic specs, and you should have them in your CAD packages with all the various footprints and everything, and different manufacturers in the related BOM items. And then when you're designing products, you can just drop in these parts. Oh, I need a regulator, I need an op-amp, I need a comparator, whatever it is. You can just pull it from your Jellybean components library and just drop it in there, knowing you're good to go. Bob's your uncle. First up is linear voltage regulators. None of that low dropout rubbish either. This one is an absolute classic. You've guaranteed to have already used this thing. But it is the Jellybean part. When you think of a Jellybean voltage regulator, you think of the 7805 or the 78XX series as it's called. And as you can see, date up here, May 1976. Yeah, this thing's been around forever. You can get it from countless manufacturers, but this is a classic fixed voltage regulator. So the 7805 is the 5 volt regulator, 7812 is 12 volts, 7815 is 15 volts, and there's other little variations in there of different voltages, but really easy to remember, classic part. They're almost bulletproof, and you should have these in your junk bin, just ready to go at a moment's notice in all different types of packages for any scenario. Output current, well, this particular one's up to 1.5 amps, but generically, like the 7805 is typically a 1 amp regulator. So if you limit it to 1 amp, then you'll be able to go across more manufacturers. It's got thermal overload protection as well. So if it heats up, you didn't have adequate heatsink, or there's some fault in your product or something like this, this thing will safely shut down if it gets too hot. But if you get in there, something's horribly wrong. And it doesn't matter if you short circuit these suckers, they're short circuit protected, no worries. And it's got safe area compensation, and what that means is that it will automatically reduce the output short circuit current based on the voltage drop across the regulator. It's another protection mechanism, really quite nice. So yeah, they're incredibly simple to use. Just voltage in and you get your fixed voltage out. You can actually use these as adjustable regulators, but you generally don't. We'll look at adjustable regulators in a minute. And contrary to popular belief, you do not actually need an output capacitor on these for stability. You don't actually need this 0.1 microfarad on the output. It's actually stable with no output capacitance. You don't need it. And you actually don't need the input capacitor either, unless the regulator is a certain distance, a large distance away from your input filter cap. But as a general rule, you just put like caps on the input and output, just because warm fuzzies. So it comes in various prefixes. There's the UA here, which is classic, but also TI also do the LM 7805 as well. And it's also known as the LM340 as well, but that's not as generic across different brands. It's just like the 7805, but they're basically identical. And they come in many different packages, which is another Jellybean trait. Old school TO3 here. Oh yeah, thank you very much. Or of course the one you're most familiar with, the TO220. But one of my personal favorites, the SOT223 here, or the D-Pack. And then, as I said, it's available from every obscure manufacturer you've never heard of. I just picked a couple at random. A Pulup. Pulup? Or I love this one here, Blue Rocket Electronics. Fantastic. Like, everyone's got a 7805. It's so Jellybean. And as far as accuracy goes, you can get them down to the 1-ish percentage region. On semi, for example, do 1.5%, 2% and 4% tolerance ones down here. But generally, they're well under 5%. They're in the couple of percent region. So your 5-volt regulator is going to be easily within the 5-volt TTL spec of plus minus 0.25 volts. No worries. And if you're wondering what's typically inside one of these, well, look, it's just a Zener here and a resistor, and then that's just an emitter follower there, and then it just does some business, and that's Bob's your uncle. Gives you your output voltage. No worries. And specifications like line regulation here, it's pretty good. Load regulation, it's pretty good. Quiescent current, it can take a little bit there, so they're not the best solution for like low power stuff. Yeah, the TIUA is like 4 milliamps there. Anyone doing any better? Over here, it's only going to specify a maximum of 6, you know, meh. How does the Pulup stack up? Quiescent current, yeah, 4 milliamps. And you can actually get higher peak currents out of this, like, you know, 2.2 amps, for example. So, but yeah, you treat this as a 1 or 1.5 amp regulator. Once again, if you're using Jellybean parts and then you're worried about things like this, or you're designing your product around a particular spec in here, then you're not really using a Jellybean part. You're not in the Jellybean category. The whole idea of Jellybean is that you can just, yeah, no worries, I'm in a pinch, I can just throw in a different manufacturer and it's gonna work. You don't even have to worry about the specs. So if you are quibbling over, oh, this variant from this manufacturer is, you know, is tighter than this manufacturer here on this spec, then yeah, nah, you might as well choose something else. And it's a positive voltage regulator. If you need the negative voltage regulator, it's the 79XX series. Once again, I won't go through the data sheets. They're just the negative versions. Consider them exactly the same as the positive 78XX series, except they're designed for negative rails. So we salute the 7805, probably the Jellybean component for like 45 years at least, still used in I don't know how many billions every year. It's just crazy. So open up any product that doesn't have any like strict spec requirements. If you need a voltage regulator, you're going to find a 78XX and a 79XX regulator in there, almost guaranteed. Now, if you need an adjustable regulator, that brings us to our next Jellybean part, the classic LM317. You should definitely know these, should have these in your kit ready to go because they're used absolutely everywhere. It's got all your favorite specs from the 7805, 1.5 amps nominal. It's got short circuit current limiting. It's got thermal overload protection. It's got the safe area compensation, etc., etc. It's got more than adequate performance on noise, power supply rejection ratio, regulation, and all sorts of things. And oh, look at all the applications. Oh, look, if you're building your femto base stations, this is the ticket, laddie, let me tell you. These are incredible. Like, the application stuff is just, it's so funny to just look at data sheets just for the application things that they put in here. It's just ridiculous. Now, of course, why do they just put a battery charger circuit? Normally you don't have the output series resistor here. You just have the 2 resistors here to set the value. The formula's in the data sheet, won't go into the details, but voltage in, voltage out. The good thing is it can go to 1.25 volts because it's got a 1.25 volt voltage reference in here, and we can have a look at the internal diagram. There it is there. It's got an internal 1.25 volt reference, so you can go down to that. So that's very useful for all sorts of modern electronics with low power supply rails. And the good thing about having an adjustable regulator in your Jellybean kit is that you only have to stock the one part, and then you can use it for all different regulation voltages that you need. Because the 7805 78XX series, it only goes down to 5 volts. Can't use anything under that. But the 317, it'll go up to 37 volts here. So anywhere from 1.25 to 37, absolute killer. All you need is 2 resistors in there. It's available in all your favorite biggie packages like this. And once again, this is not a low dropout regulator. We'll have a look at that in a second. One of the downsides is it does have a lower dropout voltage. Here we go. Oh, input to output differential voltage, 3 volts minimum typically. So that's more than the 7805. So, but once again, this is not a low dropout regulator. Just be aware though, there is a big trap for young players with the LM317, and this is the minimum load current to maintain regulation. And given that it's a voltage regulator, you want to maintain regulation. That's kind of its job. And so you need 3.5 milliamps minimum. So that's still on par with like the 78XX series, which didn't have a minimum load current, but it had the higher quiescent current. So it's effectively like, it's neither here nor there. They both are the same in that regard. So you need that minimum current. So if you're designing micro power circuits and stuff like that, these aren't the regulators for you. So if you actually do want to use the 317, and you do actually only want to draw like 1 milliamp from it or something like that, then you're going to have to put a resistor on the output to get that minimum current. I do actually like the onsemi data sheet a bit better here. Now, this is the typical application circuit. Once again, you do not actually need the output capacitor for stability, but you put it in there as a matter of course. You just need, usually this is a fixed resistor. 240 is the nominal value, and then you put your adjustable resistor in here. So a good thing for your bill of materials, if you're using a Jellybean component like the LM317, you always have a 240 ohm resistor like loaded on your pick and place machine, ready to go for all your LM317s that you use in your circuit, and then you try and like reuse that 240 ohms somewhere else. Yeah, you might typically use that then elsewhere in your circuit. You might find you need, a 220 ohm somewhere in your circuit, but I've already got a 240 for my LM317, so I'll just use it elsewhere in the circuit. Parts consolidation. And it shows the packages you can get here. TO220 Classic, of course, the SOT223, the D-Pack, and there are others available. But this is where there is actually multiple versions available. This is the LM317M, and this is only a 500 milliamp version. So the regular LM317, an amp and a half. The M version is 500 milliamps, and we'll have a look at a lower power version shortly. And there's your classic formula there for calculating your voltage output, and you can rearrange that for your resistor for generating like R2 here. No worries. And the LM317, along with this 7805, actually 78XX, is you can turn it into a constant current regulator by just simply shorting the adjustment pin out to the output, and then putting a single resistor in here, or in this case a pot for adjustable, and that makes a really neat constant current circuit. And for like an SLA battery charger, for example, you might put this constant current limiter circuit in series in front of then a voltage regulator, so you have constant voltage and constant current modes. And that's a classic, like, you know, sealed lead acid battery charger circuit. So there's the 1.5 amp version, there's the M at 500 milliamps, and there's also an L, 317L, and that's a nominal 100 milliamps as well. Apart from that, pretty much identical, and you'll find these in lots of low power circuits. But this is not really a low power regulator. It's just, I love my LM317. It's Jellybean. I want to reuse it, but I only need like up to, 50 or 100 milliamps, something like that. You're whacking the LM317 instead. It's a bit cheaper. But the good thing is the packages are small scale as well. SOIC, TO92, absolute classic. There's a SOT89, and there's a TSOP package as well. So there you have it, the LM317, the absolute classic Jellybean adjustable voltage regulator. And you still find it used in its millions, probably even billions today. Now, the disadvantage with the two previous regulators we've looked at is that they're not LDOs, or what's called a low dropout voltage regulator, because as you saw, like 2.5 to 3 volts voltage differential, you've got to have minimum across that regulator. Not only does that dissipate a lot of power, but in a lot of circuits, and especially if you've got cascading regulators, like one regulator power from another, etc., you can find that you just don't have that differential voltage margin available. So you want a low dropout regulator. And you could argue that this one, the 1117, don't worry about the TLV. Once again, there's different letters in front of them. It doesn't matter. It's known as the 1117. This is our Jellybean low dropout voltage regulator. And the good thing about this is that you can actually get it in, it's adjustable and fixed. So you can get the adjustable version just like the LM317. In fact, the pinout is identical, and the formula for calculating the resistor divider down here is absolutely identical. You can think of it as just a low dropout version of the LM317 or 7805. So you could argue that the 1117 is probably more ubiquitous these days. I don't know, like doing teardowns of stuff, I'm still seeing the 317 and the 7805, but the 1117 is just like low dropout can be really nice sometimes. So a lot of designers, a lot of companies will consider the 1117 as the Jellybean version because it has sort of like all the advantages of the 78XX series and the LM317, but lower dropout regulation. But it doesn't come without any downsides. The downside is that this output capacitor here is absolutely critical. Stability of low dropout voltage regulators, not just the 1117, but low dropout voltage regulators in general, is that, they can become unstable if you don't meet the output capacitance requirements or the output impedance requirements. And you'll see this in the typical application here. Look, the back protection diode here, this is the same on 317 and 7805 and stuff like that. You've got your voltage divider here, which you adjust with R2 down here. The formula is identical, and you can include an optional capacitor across the just pin like this. And C note B, here it is. There you go. It can be used to improve the ripple rejection ratio. But then you'll notice it says if C adjust is used, it's optional, but if you do use it, then the C out must be larger than C adjust. Otherwise, it's going to get the heebie-jeebies and go unstable on you. So 100 microfarad output cap, and that's one of the disadvantages because output capacitors, while voltage divider resistors, they're cheap. The output capacitor requirements that match the stability, the value, and the impedance needed for to make your regulator stable can often come at a high cost. So Jellybean typically implies lower cost. But anyway, with low dropout regulators, you don't get a free lunch there. And often there'll be an entire section in a low dropout regulator datasheet actually devoted to the output capacitor selection. In this case, I've got output capacitor selection is critical for regulator stability. Larger C-out values benefit the regulator by improving transient response and loop stability. Device is designed to be stable with tantalum and aluminium electrolyte caps with ESR between 0.2 and 10 ohms. So once again, it's not just a matter of having the correct value or the minimum value capacitance there. It's got to be the right type of capacitor, and it's got to have the right equivalent series resistance. If you don't get that right, especially in transients and stuff like that, like it might work fine during normal operation, and then you might get a transient and whoop, if your capacitor's right on the edge of your stability requirements, then your regulator can start ringing and become unstable, get the heebie-jeebies and go blah, 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 blah. So just be careful with low dropout regulators, not just the 1117. And they also give layout requirements here for a reason. So yeah, you want to keep your loops a bit tight. So I said they're available in fixed voltages as well, so you might keep a stock of those just available so you don't need the resistors, especially if you're space critical, you can't afford the resistors in there to adjust it. And they typically add a dash on the end of it, so dash 1.5, 1.5 volts, 1.8, 2.5, 3.3, 5, and again available from countless different manufacturers. Here's a data sheet for the cheapest one I could find on LCSC, and it's from Shenzhen Tofu Semiconductor Corp. It's all in Chinese here, you know. and there's the regular packages available. Once again, they have them in the fixed versions, as well as just they put the ADJ on there for the adjustable version, and it's the same part. You can just drop it in. You can get it from dozens and dozens of manufacturers. I almost forgot to tell you the dropout voltage. It's going to be as with all regulators, it's going to be a function of the output current. So they usually specify it here at different output currents. So at 800 milliamps, it can be up to 1.2 volts. So just consider it like under 1.2 volts here. What does this cheapie here say? 1 to 1.1, something like that. But if you factor in 1.2, that's good enough. But the 1117 is not the lowest dropout voltage regulator. Like if you need like in the order of 50 millivolts, 100 millivolts dropout or something like that, there you're going to have to choose other parts. But this is it is significantly better than the 317, that's for sure. So this is more than capable of, for example, having like a 3.3 volt rail using the 1117 after like a 7805 or something like that. Whereas you couldn't use an LM317 there because it would need that like 3 volts voltage drop minimum. So you just can't get your 3.3 volt rail from a 5 volt rail, for example. Next part we're going to take a look at is a voltage reference, or in this particular case, a micro power shunt voltage reference, because often you need a better precision, better temperature coefficient than you can get with a voltage regulator. A voltage regulator, okay, you've got an LM317 and you can trim it to whatever voltage you want, and you can use it as a voltage reference because you've trimmed it, and the one you can get them in 1.5%, that might be good enough, but often you want better than the couple of percent initial accuracy you can get from a voltage regulator. And more often than not, though, with a voltage reference for things like ADCs and other precision comparators and stuff like that, you're doing like detecting voltage threshold levels and doing all sorts of other things, you need a voltage reference that is not only initially more accurate than a voltage regulator, but also has a lower temperature coefficient. And the one we're going to take a look at is the classic LM4040 and 4041. And once again, these date way back. I've got a microchip one here because it actually combines both versions in the one datasheet, which is nice. But of course, we could go to the TI datasheet here and LM4040 precision micro power shunt voltage reference. And it looks and acts like a Zener diode. In fact, that's what they actually, that's the symbol that they actually show here. But as you saw, that's actually not what's inside this thing. It actually contains an op amp, some transistors, and like an internal precision Zener and stuff, and like an output driver as well, so it can sync some current. So these act and look like a Zener, but they're way better. So these 4040 micro power references, it's the Jellybean go-to part. You can get them in various different grades that range from like only 1% accurate down to like 0.1% or so. So right off the bat, its initial accuracy is better than a voltage regulator. But when you actually want a voltage reference for an application as opposed to a voltage regulator, you want two things. You want the initial accuracy, of course, but you also want, and often is the most important thing, is temperature stability. Now, actually, things like the 7805 aren't that bad in terms of stability. If we go to the data sheet here, so this is the fixed voltage regulator, temperature coefficient of output voltage in millivolts per degree C, of course, it's actually 1.1 millivolts per degree C. And if you get your confuser out and put 1.1 millivolts into 5 volts and get a percentage, is 0.02% per degree Celsius, which actually isn't too bad. That's actually 200 ppm. That's, is almost practically as good as a bottom of the range voltage reference chip. But a voltage reference doesn't need to deliver a lot of power, so let's go for an adjustable voltage regulator, which is the 317L here, and the low power jobby. And temperature stability here, you can see that it doesn't specify per degree C. It just says 0.7% VO, and well, okay, yeah. It's poorly specified too, because when you're talking about references, you're talking about ppms per degree C. You want to know exactly what the temperature coefficient is, not just some, typical. Look, they don't even give you a maximum figure here. It's just, it's hopeless. Nothing's guaranteed. This is why you can use a voltage regulator as a crude voltage reference. If you trim it, it's okay, but it'll get you out of a pinch. But yeah, voltage references are where the action is. So if you go over to the Jellybean voltage reference, the 4040, you can see it specifies 100 ppm. You can get like a D grade one at 150 ppm per degree C, and it specifies that, and it'll actually guarantee that it'll give you a maximum. So not only is that a banner specification at the top of the datasheet, that's how you can tell it's important, it'll also be a banner spec here, and it'll give you a maximum. Here it is, 100 ppm per degree C. So they've actually been rather generous, because often datasheets can be sneaky and they'll put like the banner specification right at the top of the datasheet will be the typical figure, but they've actually put the worst case. The typical figure is actually in the order of like tens of ppm, right? 15 or 20 ppm here. And when you're designing stuff, you should be designing about your maximum to take into account your maximum worst case specification, of course. But in this case, like typically, like this is an order of magnitude better than a voltage reference in terms of temperature stability. And that's what you care about with a voltage reference. And as you can see here, you get different grades from 1% down to 0.1%, depends on how much you want to pay. And they come in various fixed output voltages, which are really handy. 2.5 volts is probably like the most common, but you can actually get 5 volts if you want a precision 5 volt reference. And you can actually use these voltage references as low power precision voltage regulators. So if you've got, say, a microcontroller that uses your voltage rail as the reference for its internal analog to digital converter, for example, and it doesn't have an internal reference, or you want a better one than what the internal reference is, so you can actually use one of these voltage references as a voltage regulator, provided of course that you don't exceed the maximum current of these things, which is usually like 10-20 milliamps, in the tens of milliamps region. But if you've got a low power product, you can actually use a voltage reference as a voltage regulator. Pretty cool tip. And they don't call it micro power for nothing, because these can operate from 45 milliamps to 15 milliamps, i.e. that depends on the resistor value that you set here. So if you're designing low power circuit and you need a precision voltage reference in there, then you can set, then choose this resistor for this basically quiescent current here to be as low as 45 microamps, and it will still maintain its reference and specs. But sometimes, of course, you want to tweak a pot on there to actually get a precision reference. You want to calibrate your product to get that precision reference and then have it stable with temperature. You can't, unfortunately, do that with the 4040 because it's just got the single resistor like this, and you get what you get and you don't get upset, as they tell the preschool kids. But you can get the LM4041 here, which is the same, basically the same part, but it has an extra pin on here. It's got a feedback, it's got an adjustment pin, and you just use a resistor divider here, and Bob's your uncle, you can set whatever output voltage you want, well, within reason. So this is actually a good time to learn ppm here, because if you go into, like, it depends on the data sheet, and they can vary. Like, it specifies, okay, for the 2.5 volt part here, for example, it tells you, yep, it's typically 2.5 volts, and the tolerance is, it tells you that in millivolts. So if you want that in percentage, you have to take that. So if you get your confuser out, what is it, 12 millivolts divided by 2500 equals dirt times 100 equals 0.48%. So that's, you know, basically 0.5% accurate part for that one at 100 microamps. So it varies, and you might have to look at some characteristic curves if you're, you know, really getting into the nitty-gritty detail of it. But as I said, Jellybean parts, typically, if you're worrying about the real nitty-gritty detail, you're probably not using a Jellybean part. You're probably specifying in a slightly better part. But as I said, yeah, learn your ppms, because parts, which is parts per million, because it'll give you typically your coefficient in parts per million, or it might give you accuracy in part per million. It depends on the manufacturer. Other good thing about them is no output capacitor required. You don't have to bypass them, and it tolerates a capacitive load as well. As I said, if you're using these as a voltage regulator to power your circuits, you might typically have like still have some bypass caps on your chip. This is going to tolerate any bypassing on your supply rail. And we won't go into noise and things, but these aren't like the lowest noise reference parts. They're just Jellybean parts. They're, you know, in the same order as like a voltage regulator, for example. But yeah, the specs are quite adequate. So if you just need a basic voltage reference from an analog to digital converter, or maybe your microcontroller using the internal converter, it might have an internal reference. You might need something a bit better than that. Well, the baseline one you're going to go looking at is the 4040 and 4041. And as I said, they are available in different grades at different price points, so you might want to choose one of these at a higher grade, pay a little bit more cost, but you might get more initial accuracy, you might get slightly better tempo, and all this can vary between the manufacturers, and there's lots of manufacturers that'll make you a 4040 and 4041 equivalent part. And there's lots of cool application examples for the 4040. You don't just have to use them as a voltage reference, but because they're a precision part, you can do like precision clamps and things like that. This one over here, it's got like a current source. You can do that, or you can use these as a precision like a high power precision regulator in combination with a series pass transistor. And determining the resistor value here, it's not trivial. You have to take into account, just like with a Zener, I've done videos on, at least one video on Zener references. So you've got to take into account the current IZ here and also the load current you're trying to drive. Usually you'd be driving like a high impedance ADC input or something like that. So the load current here is kind of negligible, but as I said, if you're using it for a precision voltage regulator, for example, then, you know, powering your circuit up to like 10-15 milliamps or so, then yeah, you've really got to take that into account and choose the right RS here, and there's the formula for it. And just be careful if you are actually using this as a regulator to power a circuit. If you've got like large changes in your circuit current, you know, you might turn on LEDs or something and they go up to like 10 milliamps or something like that, and then it drops and your circuit drops down to like 100 microamps, then that can upset the apple cart with RS here, and you might have to do something better like a series pass transistor or something like that. And these come in through hole and surface mount, usually a TO92 old school, standard SOC23, or a smaller SC70 if you're really crammed for space. Okay, I saved the most interesting component to last. It's yet another precision programmable reference. It's the TL431 here, and you might think, well, how is this different to the like 4040 adjustable regulator here? It looks exactly the same. It's got a VREF pin, but the TL431 is used everywhere. It's once again, it's practically definition of Jellybean part, not just as a voltage reference, but in many different circuit applications. It's used in practically every isolated main switch mode power supply on the market, for example, because it's just simple and flexible and versatile, and you can use it for a lot more applications than you can the 4041 adjustable programmable reference. So let me show you what's going on here. This is the 4041 adjustable reference like this, and you'll notice that it's got the pass transistor with the op amp, and this is the TL431 here. It looks exactly the same on the surface. It's got the pass transistor here, it's got the op amp here, and it's got the internal reference, in this case 2.5 volts or bust. You don't get a say in it, but there's something a bit different in the topology of what's happening here. You'll notice that the reference input here is basically going directly to the non-inverting input of this op amp here, and there's no internal feedback at all. It's operating in completely open loop mode. But you'll notice that the 4041 here, the non-inverting input, we've got a current source here with a transistor, and we've got another current source up here. So it's not completely open loop like you've got on the TL431 here. They're actually subtly different topologies, which makes a big difference in the applications for this circuit. So this op amp here is effectively a comparator, and the output here is either going to be a 1 or a 0, effectively 1 or a 0. It basically means this series pass transistor here is going to switch on or off. Fully on, fully off, that's basically it. Depending on whether or not the external reference input voltage is above or below the internal reference 2.5 volt voltage reference. So it's you're going to get a switch in waveform like this. Then you've got the internal schematic over here, which is significantly different to, if you compare it to the 4041. I'll leave that up to you playing along at home. And you'll notice that it's also got a reverse biased diode here. Very handy for certain applications. You don't get that on the 4041. But you can actually close the loop by tying the ref pin up to the cathode up here, just like they showed at the start of the data sheet, and you put a series resistor, and it's going to act just like a shunt reference. You're going to get your 2.5 volts out of here. The reference voltage, how does this work? Well, if you remember your op-amp theory, we've got our 2.5 volt voltage reference, our anode's going down to ground here, okay? This op-amp is going to do whatever it needs to do with this pass transistor to make the two inputs the same voltage. So if our ref pin's tied to our cathode here, then this op-amp is going to do whatever it needs to do to drive this transistor to make sure the non-inverting and the inverting inputs are the same, i.e. 2.5 volts. So you're going to end up with, you've got your resistor like here, like this, you're going to end up with your 2.5 volts out there. So it works as a basic shunt regulator in that closed loop mode. But the beauty of the 431 is that you don't have to use it in that mode. In fact, if you're just using it as a shunt reference, I don't know, should you use the 431 over the 40? I don't know, it depends. Is it cheaper? Meh, whatever. Anyway, the whole idea is that the reference input here is uncommitted, so then you can actually use it as a comparator, and that's what it's useful for, like power supply feedback and things like that. Now, it's not as precision as the 4040, 4041 because, you know, look, a B grade part here, standard part is 2%, it goes down to 0.5%. You might be able to get a bit lower from that from some manufacturers, but it's not like designed as like a really precision voltage reference. It's like a good enough precision programmable reference, but it's not as good as you can get in the grades in the 4041, for example. But its current sync capability, it can go up to 100 milliamps, so it's order of magnitude better than what you can get with the 4041. As far as temperature coefficient goes, it's pretty decent, but they don't really often tell you it in ppm to compare it to like the 4041. But this onsemi datasheet does, it's 50 ppm typical, and if you actually search for ppm, it should give you like the formula used for that. Let's have a look. There you go, digest that to your heart's content. But basically what pops out at the end is roughly 50 ppm per degree C. So that's not too shabby. It's better than your standard 4041. Not as good as your highly spec'd 4041s, but not bad at all. And the reason you have to do these calculations here is because it really only tells you the temperature deviation over the full range, basically the change in total millivolts over the full temperature range. So you've got to take the temperature range and then work it out. It's annoying, but yeah, roughly 50 ppm, not too shabby. So it's available in the popular packages. TO92, very common. If you see a TO92 in the secondary side of a main switch mode power supply, then it's most likely a TL431. It's available in SO8, old school dip, and a micro 8 rubbish. So you can use it as a basic shunt regulator reference, like adjustable, like this if you want, or as I said, a fixed 2.5 volts. But where it comes into its own is all the different applications you can use it for due to its slightly different topology compared to the 4041. So here's a precision high series current regulator, for example. Once again, they've got a Darlington configuration here for like series pass transistor there. It's got a, you can use it with a 7805. You can do this with like the 4040 as well for some of these things, but you know, a high current shunt regulator, another series pass transistor there. You can get a crowbar circuit, which is common on like high quality power supplies. They'll actually short the output of the power supply and pop the fuse or whatever protection system you got in there instead of destroying your equipment. If something goes, if your voltage on your power supply goes, say you got 5 volts, if it goes above 5.25, which is the, you know, nominal TTL output, the crowbar can switch on and that can protect your $10 million board that you've got connected up to this wimpy little power supply. So you can use it with the 317 here. You're going to, once again, a simple series pass transistor. This one's simple. You can actually, a precision 5 volt regulator. You know how I told you the internal reference is 2.5 volts? They're exactly the same because the output will be double the voltage reference here. So if the internal reference is 2.5 volts, you'll get your 5 volts out here. And because this is an emitter follower transistor here, the output voltage, yeah, it'll be twice that. So nice little shunt precision 5 volt power supply. They got a PWM converter with reference here. What else have they got? Look, they got a voltage monitor here. So, you know, the LED turns on when the voltage limit is there. There are voltage monitoring ICs out there, but hey, you can use the TL431 because could you class any voltage monitor as a Jellybean part? I don't know, or some of the TI parts maybe, but they're not really fall into the Jellybean category. We've got a delay timer here. We've got a precision current limiter here. Got a precision constant current sink. But where this puppy actually shines is OnSemi have an entire like little application note here on its use in control of switching power supplies as the feedback reference part in here. And they go into the details. I can link this in, but basically, how is regulation performed? Textbooks only describe op-amps in compensators. The market reality is different. TL431 rules. And sure enough, there it is. The TL431 is the most popular choice in nowadays designs. So yes, it basically does optocoupler control. Of course, you need isolated feedback. You've got your switching transformer and for your mains power supply, and then your optocoupler feedback, and it's tied into the optocoupler feedback here, and it's absolutely perfect for that. And you can control based on these resistor values here whatever output voltage you want. And they go into all the math behind that, but yeah, check it out for yourself. Bias currents can be a big problem. And there's small signal analysis for all you small signal analysis fanboys, and it can get rather complicated. But because this part is the Jellybean part in almost every mains switch mode power supply out there, yeah, all this stuff matters. Jeez, now we're getting serious. Look at this. Whoa. Anyway, that's crazy. I'll have to link that one down below. Speaking of which, TI also have a design with the advanced TL431. Here it is. Here's once again the isolated feedback from the secondary side of the switch in power supply and how it drives the optocoupler feedback there. Now, here's one of the traps for young players. You know how I said the TL4041 is stable with capacitive load? Well, unfortunately, the TL431 is not. So you've got a stable region and you've got an unstable region, just like with low dropout regulators and stuff like that. You can't just whack a capacitor on the output and it's, yeah, not going to be stable. There's going to be an unstable region there and you can completely kamagatsa. I won't go into the details, but I will also link in this data sheet down below for application note down below. Suffice it to say that yeah, if you don't get those, the capacitance right, you can really kamagatsa, and it can go unstable and ruin your day. But there it is. There's the isolated. There's your isolation transformer and your optocoupler feedback for your mains input power supply. Cool. It's a very versatile part. There's tons more applications you can use it for. Bonus part, because the fanboys won't let me off the hook if I do a top 5 list without the Ref 01, which is basically the Jellybean really ultra precision reference. So how good is it? Well, it's, its typical accuracy here is not that great, but the whole idea is that you can, trim it to exactly what you want. The good part about it is, look at this, 8.5 ppm per degree C maximum schmick as. So you'd use this in like precision converters, precision references and stuff like that. If you need something better than the 4040, there are better parts out there than the Ref 01, but it is the Jellybean part. And there's one cool thing about it too, is not only does it have a trim input here, so you can but it also has a temperature output as well, a temperature compensation output. So you can use it as a temperature reference, not only for your own system, like a temperature sensor for your own system, but then you can also use it to compensate for the reference as well. You could potentially feed it back and... So there you go, the output voltage of the temp pin is taken directly from the band gate core and as a result varies linearly with temperature. So there you go, you could buffer that 1.9 millivolts per degree C and you could potentially compensate for that like 8 ppm drift of this thing if you really wanted to. Neat. And because it's on the die, directly on the reference itself, you don't have any thermal effects inside your case. You don't have to like strap a temperature reference to the can of your voltage reference and stuff like that. It's built in. It's a pretty schmick part. So there you go, that's my top 5 or so Jellybean voltage regulators and voltage references. I'll link them in down below, and I hope you enjoyed that. If you did, please give it a big thumbs up. As always, leave comments down below. You can't dislike videos anymore, apparently, because YouTube has disabled the thumbs down. Bastards. Done a video on that. I'll link that in too if you want to see it. Unbelievable. Having said that, check out my Odyssey channel, over 64,000 subscribers over there doing gangbusters, and you can leave a splat or a dislike if you don't like my video, unlike bloody YouTube. Anyway, if you want me to do another top 5 video on another like set of components, let me know in the comments down below. Hope you enjoyed it. Catch you next time.